Good evening, very good evening to all. Myself, Dr. P. Kamaraj, scientist engineer SF from National Atmospheric Research Laboratory, Department of Space. Okay, actually, past 20 years I am involved in this domain. So my major contribution to our center is I used to develop active phased array radars. And recently, what are the new developments happening in the VLSI as well as FPGA side? That also we are trying to implement it in the excited development as well as signal processing side. Okay, so today I am going to present like this. This is the outline of my presentation. I think all of our faculty members, they know very well about this fundamental and all. Even though still what I am feel, so this some fundamental theory should know about RF engineers. That is what I am mapped like this. So first thing is RF fundamentals. Second block is basic blocks of an RF system. Then RF simulation software, because we are designing any system means we will not directly, we are not going for hardware designing. Before going to hardware, whatever antenna design or power amplifier design, whatever may be, we have to concentrate. First, you have to do in the simulation side. Based on the simulation result, aptitude result, then only we'll go for fabrication and all. So that is what I will give some introduction about RF simulation software also. Then next thing is AIR system. AIR system is nothing but a advanced Indian MST radar system. So this is the radar. It is in our country is a globally second biggest array radar. Here we have 1024 elements presence here. Actually, 1024 numbers of Yagi-Uda antenna. This is all the second biggest radar. So in that, first this radar designed 1992 by using a vacuum tube based transmitters. Now at present, last 10 years we took a project, we modified, we upgrade the system, vacuum tube system to solid state, because the vacuum tube we are not able to get the components and the tubes and all obsoleted. Because of that, we are forcing to develop the new radar by using of solid state. So that one I will explain. Then the next thing, recent development of RF SoC. So RF in SoC, that means system on a chip. In olden days, no, you know better way, because I think many of them are involving in the developing a receiver system and all. Analog system was there. After the digital system, digital receiver came. In the digital receiver also, timing, signal and all generation by using of FPGA plus signal processing, like for we want to do for FFT, fast Fourier transform and all. They are always using a Tiger Shark processor, like a DSP processor. But nowadays, last 6 or 7 years back, we have a technology called a SoC technology. In that FPGA itself, we can generate a RF signal. So next application of, so based on that, we developed 2 systems. In that, I will give a small introduction. I will give about RF SoC. So because see, this RF SoC, many people may be having a knowledge about that, because any upgradation is also there in the audience side. You can tell us, because we have to improve ourselves also. Okay. So next. So as I said, first thing is fundamentals. In the fundamentals, all electronic engineers or faculty, whatever researchers, whoever, so they should have a knowledge about electromagnetic spectrum. Because once the person knows the electromagnetic spectrum, then only they are able to design the whole system. Because this system, any system or antenna or a power amplifier, or any circuit, the size of the total system depending upon the frequency. From the frequency, that will be decided by the wavelength. You know that F is equal to C by lambda. Based on that only, we are going to develop the antenna. You know, antenna size also a lambda by 2 kind of things. Because of that, we all people knows, that is electronic communication engineers should know, aware of this electromagnetic spectrum. This electromagnetic spectrum in that, especially in the RF field, very low frequency to extra high frequency. In that particularly that VHF, very high frequency to EHF, it is having the all sort of communication system like radar band. They used to call a radar band LSCXKU, that KU, K, KA, W, and B. So that is radar band. Next slide, I will explain that one. In that, always in that FCC standard, they are allowed for some frequency bands. Like FM transmission means 88 to 108. After that, FM frequency band, military application as well as our researcher will take it. Additional to that, ISM band is there. ISM means industry, scientific, and medical. These instruments will having some frequency band. That especially that 2.5, 2.4 gigahertz they used to use, that Wi-Fi frequency, and you know very well about that. So that and all frequency, that information you know about the while designing the any systems. So this is the radar frequency band. So L band, you know, 1 to 2 gigahertz, S 2 to 4 gigahertz, E 4 to 8 gigahertz, X band 8 to 12 gigahertz. In our curriculum, in our in BTech or MTech maybe, so they will in microwave lab they used to do that X band. So X band 8 to 12 gigahertz. Why they especially they gave X band? So not C band, S band and all. X band. So only thing is that the medium. In low frequency, you can use normal coaxial cable, but translation is happening in the X band onwards, because X band and all you have to use the waveguides, because that the difference has to know about our teacher or students or whatever it may be. That is what in microwave lab and all they are using a klystron and all X band thing. So that one you see. Now next to KU, KA, and VW band. These are satellite band. So why? Because it is called a satellite band. Because this you can see that the wavelength in the range of 1.1 centimeter. Because of that miniaturize, we can develop. Because yesterday also, the day before yesterday, 2 or 3 speakers talked about only micro 6G antennas and all. They are designed by using a K band or K band or KU band and all. So because the miniature size, we are able to design antennas. Suppose in case of low frequency or very low frequency, high frequency, very high frequency, these are ranges and all, we can't use the microwave, microstrip patch antenna or other small miniature antennas. You have to go for Yagi antenna kind of. This difference you should know about. How you know means you should know about this frequency band difference. What is radar band frequency, satellite and all, what type of frequency they are going to use, that information should know. So all the electronics and communication engineers should know about frequency and wavelength. That relay these two things. If you are in, you know very well means you are able to understand the system. You can able to design the new systems. Next thing is RF cable. This also, you know, in our college side and other normal commercial and all, they are using a BNC connector cable. That is sometimes it is a 75 ohm system. But if you go for industry, you have industrial grade cable like coaxial cable like LMR 400 or LMR 600, 1200. LMR means land mobile radio cable. That is for only for industrial grade. One more grade is there commercial grade as well as space grade as well as military grade. While going other grades, that quality and the cost also will increase. That information also you should know about that while choosing the cable. Because choosing the cable itself, we will have more information. Because you know that if you want to design one any antenna kind of thing, in that what type of balanced and imbalanced you are going to use, unbalanced you are going to use, means there you have to choose that wavelength type. So wavelength also you have to particularly that wavelength is not a lambda G should be there, guided wavelength. For that you have to choose particular cable. So LMR 400 or whatever maybe. So you can, this is the one chart I gave a small example. That cable, same cable performance will not the same for other frequency. Because if you take that in your screen, you can see LMR 400 characteristics. For 30 megahertz, you have every 100 meter 2.2 dB loss will be there. At the same time, 50 megahertz, if you go, 2.3, that 2.9, that is a 3 dB loss. Half of the power will be lost. Like that, if you increasing the frequency, automatically that attenuation also will increase. At the same time, power handle capacity also will be reduced. So this factor you have to see. So that is what all researchers should know about. Simply, if you want to design an antenna, by using the antenna, you are taking some other unknown characteristic cable, means you will get a wrong result only. So at the same time, so any test you have to do means you have to choose the cable, particular cable, what frequency, up to what frequency it can work. That information you should know. At the same time, what type of instrument you are going to use, whether that is for yesterday that 1 terahertz antenna designed, say researcher gave some talk. No, in that what type of instrument, because if you are increasing the frequency, the cable cost also increase, instrumentation costs also increase. So that and all you have to see, because that is what all engineers colleges and all, they will not produce this type of instruments. Many colleges are having only spectrum analyzer only. That spectrum analyzer also up to 1 gigahertz or 2 gigahertz only. Specifically, some universities only having that this type of setup. That means high frequency setup. That information also you should know. You can compare that LMR 400 and 600. You can see that see the frequency performance attenuation as well as average power. Next thing is connector. So connector also, this and all researchers will not take more importance to this type of areas, because this connector, they will say, okay, what is in that? It is a connector only. No, not like that. That connector also you have to see. Up to all connectors, all cables having a specification sheets, data sheet. In that data sheet, whether this type of connectors, whether this can be handled this much power, or there's a frequency, whether it can be used for that. That information you should know. So with various types of connections, connectors are there, TNC type. In normally labs and all, we have a PNC only, but all industrial cable connectors and all, TNC or SMA A or SMA B, this type of connector they'll use. So in that, because this connector will decide your VSWR or return loss also, it will be in that matter. So that is what, while choosing the cable, connectors or instruments, you should have some attention on that part. Data sheet you have to perfectly have to choose. Otherwise, you will get a wrong result only. So these are the instrument, RF instrument, well known actually. That is the first instrument called a vector network analyzer. In that network analyzer, you can measure antenna parameter, return loss or VSWR, S parameter, S11 or S21, all parameters we can measure. That is the application of that instrument. That next thing is commonly available for instrument is a spectrum analyzer. You know, two domain is there. One is time domain, another one is the frequency domain. Time domain signal you can measure by using a scope. Spectrum analyzer, especially you want to measure in the frequency domain, either CW signal or pulsed signal. At the time you have to see for the spectrum analyzer. From the spectrum analyzer, you can use output power, harmonics and spurious and phase noises, adjacent channel power, how much that modulation deviation, everything you can measure. Next thing is a signal generator. Signal generator is not a measuring instrument, it's a source. Source means we can give that signal level, because in the Agilent, that Agilent now Keysight will give excellent minus 110 dBm signal on to almost 20 dBm signal. Nowadays it's coming. So you have to choose the right way, what type of signal generator you have to use, what frequency you are going to. So we are going to do in the research. In that, double that frequency value you have to choose. Next is the power meter. Normally, power meter is generally power measuring method. In scope method also you can measure by using the peak to peak value from their internet. You have many table is there, peak to peak value corresponding what is the output power. That one will measure. But if you're buying a high power meter, directly you can able to see what is the output of the transmitters. That one you can measure. This is the measuring instrument. Oscilloscope, I said in colleges and all, most of the scopes are analog scopes. But In a research field, mostly they are using digital oscilloscope. A digital oscilloscope means we can see the pulse, n number of pulse continuously, which is using in the FPGA domain or other microcontroller based engineers. At the same time, we can measure phase shift between the reference signal to the what is the we are going to radiate the signal. That information also, phase difference also we can measure. These and all measuring instrument. If you want to set up one lab, this instrument compulsory present for it has will be present in the RF instruments. Next, simulation. I said so. The simulation software nowadays this is for cakewalk. So because students are once they know some about any one of the software means. From that software, they can go and join many companies because big companies, the ADS system software is the first user-friendly software, but the cost is very high. But whatever high-speed digital application or RF circuit or microwave, by using this software, we can do easily, we can design. At the same time, what are X parameter means we can, that is like S or HFE, whatever parameters we can put it in the system. In our system, we designed that solid state TR model. Before going TR model, we used this ADS only. From the ADS, we have in that ADS, we have many library function. In the library function, each and every chip having the transistor or MOSFET, whatever may be, it is having its own characteristics. If you drag it, it will give the total spectrum of the output. Either spectrum or harmonics, everything will give. That is the advantages of your this ADS software. Okay, this ADS software budget also we can calculate. What is your given input? What is the output? In between.
Kamra sir, you are being muted.
Yeah, muted, correct.
Sir, your mic is muted. Sir, your voice is muted, sir.
Sorry, sir, I have been muted.
Presenting something else, it's coming. Okay. Able to see that presentation, no, sir?
Yes, sir, we can, sir.
Okay. Sir, my flow is very faster. Okay.
No, you are going in the right way, sir. You are covering the topics right way.
Okay. Right.
Because all of us are faculty members.
Yes, that's what
catch up your points.
Okay, sir.
Thank you,
sir. That is what I put this ADS is the first because we have a better experience on this ADS. In our 1 kilowatt TR model, all the power amplifier design as well as LNA design we done by using this ADS software only. Next software is it's a familiar software actually. Yesterday and the day before yesterday also that researcher used the HFSS only. This is most of the HFSS is using for designing the antennas. In that antennas, in that software, by using this software, 3D model and full wave and electromagnetic field, what is the radiation pattern, everything we can see in that. But it's such a cost effective only. Next, electronics workbench. Most of the IITs having this electronic workbench. That means it's having a total suite like PCB design, then the circuit simulation, SpeedWise or FPGA software, VHDL, recently Vivodo, everything will be integrated in your one bench. That is now many IITs having purchasing this electronics workbench. But we have HFSS and ADS only. Next thing is PCB. PCB is now you can see in market, no small power supplies or other toys also they are making a small PCB. They will put on what you call on amplifier something. Many toys are for that forcingly they are producing a more PCBs. For that many softwares are there, especially ARCAD. That software PCB solution is a very up to one. Now we have ARCAD software as well as a PCB edging machine also is there. whatever we are producing a schematic, that directly we are able to give a total picture. For that, suppose we used to purchase any circuit from the vendor, immediately that we will take that file or Gerber file. From the Gerber file, we will put it in our PCB etching machine. Second times, we will not depending on the vendor. We used to produce whatever we want, that we will produce from the software plus that etching machine. This is the one PAD software. Next, all are familiar with MATLAB. Any scientist or any engineer we want to do in any research means, by direct first person they should know about the MATLAB. MATLAB is because in our radar field, whatever received in raw data, time domain, I and Q data, that data we are converted into as a usable form like wind speed and wind direction. That and all we are doing in the MATLAB only. We have developed one ADS software, that is ADP software, Advanced Atmospheric Data Processing Software. In that software output, we are combined with the MATLAB. We will calculate it will give the direct value of wind speed and wind direction. So that is what this MATLAB now. You know that AI and machine learning system now is coming. No, it's now trend. That all new versions MATLAB having this kind of things. Because of this, we have to upgrade our knowledge of that MATLAB. What are the many library function as well as package. Antenna also separate package is there. Now common MATLAB we purchase. Other accessories you want to design on antenna means they will provide. Like LabVIEW software, that also we have. So all researchers should have a knowledge. You should have a knowledge about MATLAB and hands-on training also. If anybody is providing MATLAB, means you acquire knowledge from that sessions. Next. This is the one complete RF system. Previous slides and all, I explained about what is the basics and all. Now, what is RF system? RF system consists of one transmitter, one receiver. Some cases, both will be combining. That's what I said, that SOC. SOC means all will be integrated. Transmitter as well as the receiver. Combined together, we will get a transceiver. That is the total RFIC it's coming. Next, all any circuits, it is two things is required. One is called VCC, supply voltage. After that, whatever timing signal or whatever your RF signal you want to generate means it is that purity of signal or rise time, fall time, all depending upon your fundamental frequency. That is a basic frequency reference signal that will be generated OCXO. Nowadays in the crystal and all they are using that. You have to take up. That is one block. Next thing is, suppose if you have one transmitter is there, it will give the one say example 500 watts it will giving. So that 500 watts, our ultimate aim is all 500 watts power it has to radiate. How it can be radiate? So through antenna, all of you know. But if you design, if you connect means it will not radiate. You have to see the functionality of the device, designing the antenna. You have to see the maximum power when it will be transferred. So, you know, maximum power theorem. So, your source impedance should be matched with the load impedance. That is what you have a design. While seeing the design, what is the source impedance? Generally, industrial area, 50 ohm. But in commercial area, the TV and all old in our household tech items and all, 75 ohm. Okay. Always you are talking about only 50 ohm. That has to match with the load. Load is nothing but of a space, because antenna has to radiate through space only. In that space, we have the impedance 120 pi. It's nothing but a 377 ohm. While designing the antenna, you have to see the match. For 50 ohm, how you have to match with the 377 ohm. In older that Yagi system and all, they used one cable. They will put a U cable. From the U cable and then folded dipole. From the folded dipole, 400 become 200. Again, one cable they are using, 200 become 50. Like that they will match. But in terms of microstrip patch and all, you have to choose the point. Then whether you have to put one LC circuit or tank circuit, whatever may be, in that you have to match the impedance. That is called a balance. Balance means balance to unbalance. Next thing, filter, whatever you required filter, frequency only component has to come, means you have to put either high pass filter or low pass filter or on band elimination filter, whatever maybe you have to put. Then antenna. I said antenna, different types of antenna is there. Why different types? Means purely depending upon the frequency as well as wavelength. That will be decided. This is the basic block of RF system. So an RF transmitter and receiver and reference signal, balun and antenna. So this is, I said, so our radar initially 1991 designed by our Samir people. At the time we used vacuum tube based transmitters, 120 kilowatt, 96 kilowatt, 56 kilowatt, like that. Various power level transmitter output were there, because you are seeing in the screen, that is the triode tubes. Actually in the big one 5000 series, it will give the 120 kilowatt output. Remaining things are 100 watt. So these are the, I'm showing that the old versions, because now present generation cannot see. I think many of the radio station or TV station are still they are using for amplitude modulation this type of tubes. Now this is coming to our third topic, advanced Indian MST radar. Seeing in the screen, that is our whole array. 130 meter, 130 meter, 1024 Yagi antennas are there. Because I said this is a globally second biggest radar. First biggest radar is in Peru. So next our radar in the class of active array. So you can see here, because I said that old transmitter, 32 transmitters were there. Because of that, each transmitter is output is connected to one row of antennas. One row. That is what that array size arrived. 32 cross 32, 1024 numbers. Now, because of that, we took a project and then we removed all the vacuum tube based devices. Then we installed in the solid state TR model. We are seeing in the hut, in that hut, we have 4 transmitters are there that will be connected to the antennas. Because of that, each antenna is connected one TR module. If any tracking radar also having the similar concept only. One antenna is connected with the one FEM. Generally in a high frequency they used to call a FEM, front end module. Okay, that is a one TR module like that. So here also we are connecting a one antenna is connected to the one TR module. Because of that it is called a active array. So previously one transmitter is connected to n number of antenna, means semi-active. One antenna directly connected to one single antenna, one TR model means active array. So in our configuration, 130 meter, 130, that 1024 antennas are there. So 32 cross 32. So in that also, we have a scalability is there. Scalability means we need not operate whole radar for any kind of experiment. We used to select some group of antenna. For that provision we gave, that is what like a group wise. We have 64 groups are there. Each groups having a 16 element. So like that we configured. I said this is upgraded system actually. In that in the only domain, in the radar domain, it's having a whole subject, like whatever you start from that semester to MTech or PhD up to that level, all the domain will be present in the radar system, any radar system, because antenna design and the TR model, and then TR model controlling by using FPGA, then power distribution. Okay, so all will be present in the one system. So here many people are doing research on that one particular domain. They will get a PhD. Many PhD also came from our system as engineers times I am telling. But application side, whatever atmospheric data they are doing a PhD, that is different level. That is scientists they used to produce and they will produce a PhD. But a system level design, many PhD we came out from our institution. This is the specification of our system, advanced Indian MST radar system. Because I said this, our main application of our radar is we are providing the wind information to the star center. While rocket launching is there, at the time, especially atmosphere having a 4 major layers called the troposphere, stratosphere, mesosphere. After that, ionosphere. Troposphere means 0 to 20 kilometer, 20 to 60 stratosphere, 60 to 100 mesosphere. After that, ionosphere will be there. Especially that troposphere region, 0 to 20 kilometer, that wind is not a unique. So keep on, it will change, in particularly that 14 to 18 kilometer, it will having a one impulse kind of wind will come. That's called a gust wind. That gust wind, if anything happens during a launching time, that totally our radar launching mission may fail. So you have to see that during launching time whether that gust is happening or not. You have to check. For that, our radar is continuously sending that RF signal, and we're using the, we'll use to monitor by operating the radar. Okay, so this radar, we are sending a 153 megahertz signal to the atmosphere. Reflection will come. Reflection will 53 plus or minus some Doppler will come. From the Doppler, we'll calculate the radial velocity. That radial velocity we used to conduct 20 kilometer up to. That is a working principle of any radar, tracking radar or whatever they are using in satellite. There are those SAR is there, a synthetic aperture radar. That principle also same. You have to send one RF signal. Reflection will come. That reflection will having some different frequency. That frequency, Doppler frequency. From the Doppler frequency, we can calculate the velocity of the target. In our atmospheric radar, our target is wind. Suppose tracking radar, a target is enemy vehicle or any other obstacles. That is the target. So that is the small introduction about radar. Okay, in this our radar having VHF range, operating frequency is 53. Total 1024 antennas are there. Each antenna is connected to 1 kilowatt transmitter. Because of that, we have a 1 megawatt power. Power aperture product. Any system, it is having, we have to see what is the power figure of merit. Figure of merit means how much power you are going to radiate. What is the size of the antenna? That is gives the PA. PA means power aperture product. Next, duty cycle. Duty cycle is nothing but our radar is a pulsed radar. Two type of radars are there. One continuous wave radar and pulsed radar. In that pulsed radar, some short of time act as a transmitter. Remaining times and all, it is a receiver. From the received signal only, we will process and we will calculate all the parameters, required parameters. Okay, so then in that 100% in the pulse, in that only 5% we are able to, you have to radiate. That is what this duty cycle will shows. Then TX and RX type is solid state. Pulse width, you can go for 500 microsecond. Range resolution. Range resolution means how much kilometer interval we want to echo. That means R is equal to C tau by 2. One formula is there. In that, if you use a 1 microsecond pulse width, we have a 150 meter. If you use a 0.5 microsecond, we have a 75 meter. Our radar, we are able to use 0.25 microsecond. Because of that, 37.5 meter resolution is there. Every 37.5 meter, we'll get a one echo. Then we'll put it in average, and we'll get a one small power spectrum. In that, we'll calculate the required parameters. Then antenna. Total, I said 32 cross 32, 1024 antennas are there. Single antenna gain is 7 dBi. Because in that Yagi antenna, we are using a phased Yagi antenna. Yagi antenna means 3-element antenna. One is top one is director. Second one is folded dipole. Bottom one is reflector. I said why folded? Because of matching purpose. 372, 77 ohm to you have to match with 50 ohm. For that first step 400, then one cable we are using that will catch it. Okay. So one antenna will give a 7 dBi gain. Then 1000 numbers, 1000 marks, logarithmic scale 30. Because of that, that 37 dBi arrived. Next, beam width. Beam width is a 2.2 degree narrow beam width. If you increasing the antenna size, the beam width will be narrowed. So that and all you know better way. Because of that, why they are making an array antenna means you want a pencil like beam means we have to go for larger array. So that is what we have a 32 cross 32. That is what we got 2.2 degree. Next thing is side lobe level. Side lobe level. Whenever radiating all the element, you have to see the radiation pattern. In that exactly we have to see that whether we are able to get a side lobe level less than minus 13.2 dB. Because otherwise, no, that side lobe level will be dominating the main lobe level. Our total signal, SNR, everything will be correct. So while designing the antenna as well as now that in recent system and all, in side lobe level reduction techniques are there. fuzzy logic techniques as well as some windowing technique also they are going to use. Mostly Taylor kind of thing they use, and then they'll reduce that side load level. That is one thing. Next, receiver and gain, 90 dB gain will be there, and the noise figure is less. You have to maintain 3 dB, less than 3 dB. Otherwise, no reflection will occur in the mode side. So now I said MATLAB. So say now you can see what is the application of our MATLAB. So this is a simulation pattern, radiation pattern. Clearly you will see that if you use more elements like 32 class and full array, in that we have a beamwidth of 2.5 dB. Suppose if you use a 16 cross 16, we have a 5 degree beamwidth. Next 8 cross 8, lesser numbers, 10.25. So while reducing the number of elements, beamwidth will be broadening. So that one only. At the same time, you can see that side lobe level also elevating. This is a simulation result. Same simulation result we verified from the natural source like Virgo and Moon also. It is one of the source to verify our radiation pattern. Practically we verified that one. So this is the simulation result. Okay. Next, this is the feeding network. I said each group having a 16 element. Here two things are there. One is RF signal, another one is what you call control signal distribution, because that TR model is like a digital TR model. Digital TR model means it is having a one control card. That control card purely FPGA based in our system, but other system also same kind of thing only. In that we have to send the signal. You have to communicate from the control room to TR model. That is happening in the optical mode. That is what we have, optical splitting network. RF is normal RF. 0 dBm, if you give one TR model, you give a 1 kilowatt. Like that, 1024 models, 1024 kilowatt will give. So afterwards, I will explain total TR model side. So this is the picture of our TR model. Whatever you are seeing is this white color. This is the MRF 157 transistor. It will give the 600 plus 600, 1.2 kilowatt output will come. This side is nothing but a TX side, transmitting side. Another thing I said no, that is a control card. Control card, FPGA based control card. Spartan 3E chip is there here. In that associate with the Ethernet PHY, because the control signal through Ethernet only it will coming. Here only speed will be matching Ethernet. All the signal will be coming to over here. Additional to that, we have a microcontroller and ADC. Why? Because we have to check the status of the TR model, whether how much power it is radiating, how much voltage is of presence, whether 60 volt for a power amplifier, other voltages are is there or not. And next thing is this is a phased array radar. Phased array radar, we are introducing the phase in the phase shifter. We have a 6-bit phase shifter. This is the phase shifter circuit. For that, all the information is nothing but one switch. Additional to that, LC will be there. In that, if you select the phase, automatically the phase shift will be happening. That information and all sent by this FPGA only. Okay. So now you can able to see here this phase pulse. That is a time domain signal, 8 microsecond pulse with that coded signal. Corresponding frequency is the sync function. So this is the TR model. Okay. Now general block diagram of TR model. I will not take much more time on this. First thing is gain and phase measurement block. Any TR model, this is the first step because a digital attenuator will be there. In that, by using that, we can reduce the input level or cannot increase, but we can reduce the level, tapering and all you want to put in by using that value. Next PS is the phase shifter. 6-bit phase shifter is based because of the phase shifter only we're able to tilt in electronically in the beam. So there only they are using a phase shifter. Then TR switch. TR switch is nothing but a isolation between a TX path as well as RX path. This is the TX path, high power. We are giving a 0 dBm here. Here it will make it as a 1 watt. 1 watt become here driver amplifier, it will make a 100 watt. After that, power amplifier model is there. 100 watt become a 1 kilowatt. Then output we are connecting to the one TR switch. In this TR switch, directly if you one pulse we are going to apply, during on time it will be TX path. While receiving the antenna from the signal, it will come on receiving plate here. Then we have to check how much power you have to radiate. There we have a directional coupler. Some part of the RF we are taking through coupler. From that we will put into make it as a digital form, and then from that information the radar control will say how much power it's radiating. For that sensing time, for that we have a circuit, power divider and detector circuit. In receiving side, any the receiver, first stage is limiter will be there, because the limiter you have to protect the LNA, because LNA, our atmospheric signal is minus 110 dBm. That much low level signal will be there in terms of 0.07 microwatt only. So it will come. Even though we are pumping a 1 megawatt power, but received signal is in terms of microwatt only. You have to amplify by using many stages of amplifier. Still, any high power entering the LNA, our LNA will be gone bad. That means burnt. So you have to protect the circuit. We have before that the LNA, two circuits will be there. One is limiter, another one is a blanking switch. Next, this I said this is a digital TR module. In that we have a control card. Control card I said that FPGA based control card. That control card function is it will give the TR pulses, blanking pulses, digital attenuator pulses, phase shifter pulses. Everything will be generated. Okay. After that, after coming slide, I will explain detailed in that. This one you can see. This is the phase shifter. We are simple sample. I gave 6 different value of phase shifter. So this green color is our reference signal. The blue color is the output of the TR module. Whenever applying one 5.2 degree, because I said this is a 6.6 bit phase shifter. 6 bit phase shifter means any resolution. We have a formula full scale deflection by 2 to the power of n. That's what. Suppose in the case of phase means 360 degree is the full phase divided by 2 pi power n. 6 bit means 32 will come. 5.25 degree will be there each 1 bit. If you put 1 bit, it will give a 5.2 degree phase shift will be there. Suppose 10, if you use second bit will activated 11.50. Like that, FF up to that value, you'll make it again 0. Like that, this is the phase shifter configuration. That phase shifter itself, one PCD will come actually. So 6 bit phase shifter. Okay, next. This is the output of the thing. We're seeing this here. This is spectrum. This is the receiver bandwidth. You can see the harmonics. Whatever this harmonics, whatever we designed by using that ADS software, we compared. This is totally matched. Minus 60 dBm level will be there always, second harmonics compared to first and second harmonics. Next thing is any output pulse, we have to see the rise time, fall time. If you rise time and fall time poor means we will not get the whatever required output. In that we used to maintain 150 nanosecond. This and all while designing time you have to check all the parameters. Okay. So these are the test results for TR model, because we are not accepting a single module result. We have to put 10 modules in the network mode. Then we will take a continuous monitoring of result. That burning set test will be there. Rain testing, many tests we used to do in the TR module evaluation time. So this is for TR module network, because I said each and every TR module having a one control card. That control card is communicated through radar controller PC to TR module is through Ethernet only. Ethernet only means you have to go for IP. So here we have 1024 IPs are there. That all will be configured. In that also, initially we put it into one control 19 TR module in the one network, because that pinging issue will be there, timeout error will come. You have to see, then only you have to clear, because the vendor doesn't know. Simply they will put it there, it's an evaluation circuit in that control card they will supply. During testing time it will come. So while operating real time operate, you have to care about pinging status and all. But that's what while integrate, while clearing this thing TR model, at the time we tested that network thing. So this is called a GUI in the typical radar GUI, radar controller GUI. Here we have a pulse width and IPP value and coherent integration, incoherent value and FFT. This parameter and all we have to put it in the TR module FPGA card. First, you have to program in the radar controller. This information will go through to TR module via Ethernet. Ethernet also, we don't have a electrical Ethernet. We have all of optical Ethernet only. Right. So this is the output of our radar. So I said no. So I say we are calculating the radial velocity and speed. That is we are giving to SHAR. Not only that application, other scientists will, some group of scientists will research doing the data from the lower atmosphere or troposphere, stratosphere. According to that, we will operate the radar. Now this is the typical one power spectrum profile. You can see here x-axis is the Doppler, y-axis is the kilometer. This is the Doppler frequency. From related to Doppler frequency, what is the velocity? That value in the MATLAB code is there. We'll take the data to the ADP software. From the software, MATLAB will convert this value to direct velocity value. That will be, we are sending the software. This is the power spectrum output, frequency spectrum. You can see here x-axis is Doppler and y-axis is the kilometer. Up to that 24 kilometer, we are able to get the data. Same way, suppose if our radar designed that is okay, it is coming, whether that information correct or not, we need a one reference system. That's what we have a one radio sonde is that I think many researchers knows that a radio sonde balloon. We used to launch daily one balloon. In that balloon, they will keep one sensor, temperature sensor and pressure gauge temperature sensor, and then wind speed sensor, everything they'll put it in one box. Then put it, tie it with the balloon, hydrogen balloon, it will go to space. So in that up to 30 kilometers, it will go and then keep on, it will give the data. We have in the ground station in our office, we have one GPS receiver. GPS tracking is happening, that at the same time, it will be receiving the continuous data. That information they plotted. You can see here correlation between our radar and the GPS radio sonde. It will be exactly match. So this is for one type of validated system, our system. This and all we done initial because we upgraded the system. No? At that time we done this thing. Additional to that, this is the multi-beam experiment. This and all okay. So next, so from this radar, not only troposphere, stratosphere, mesosphere, whether we are able to see other object. That's what we tried for that in 2019. Whether any echo will get from moon, we explored that. We got an echo from the moon. So one advantage is from this experiment, we already I shown that MATLAB radiation pattern. No, in that what is the beam width in the 2D? So that will be matched actually. What are the only we'll put it in the radar in the receiving mode. Whatever echo is coming from the moon, we collected and then we plotted the RTI map, range intensity map. We can see exactly in the during that day, 15/4/2019, exactly 9 o'clock. 9 o'clock in that particular period in our radar site that the moon was there. At the time we got the echo. So that is what we, from this experiment, whether we are able to get any echo from the moon or not. So that we done that experiment. Next thing, one more array we install in the outside our NARL campus. There are also 4x16 element antenna. Within a week we installed and then we collect the echo from the moon. This is called one type of interferometry. Interferometry means we can two system from the two system. We can calculate the radial velocity of the target. Small experiment we done that we got some echo in that. Next thing is whether any other possibilities are from this radar we're able to see. That is what we observed ISS in International Space Station. That echo we received within a 10-second. Over the radar. We got some echo. From the echo, strong echo we got. It is like confirm that ISS information will be available in the net. During that time, particular time, we operated. So we got it. So that is what one we will show that what is the sensitivity of radar. That also we calculated. Same way, one more step we put whether we're able to track the any satellite. So RB2 satellite we tracked and then small size, how much size we can detect. That experiment also conducted by this radar. we have a 1 meter, 1 × 1 meter radar satellite. We got it. That is a SARAL satellite. That also we did it. Based on these experiments, we are seeing that whether we are able to do any what you call debris detection from the scope, because now now major issue of space is it having a more junk in the space. We have to detect it, because that will go any small piece also, it will go 7 km/s, that much fast. So it will be damage live satellite. That information also we have to see. That is, we are doing some experiment kind of addition by using that AI techniques also in that. Next, optical distribution. I said totally 4 signals are there for operation of TR module. One is Ethernet TX, Ethernet RX, IPP, interpulse period reference signal, clock signal for whatever FPGA used. For that it is required clock signal, that is here 16 MHz, and then calibration signal. Calibration, any instrument or whatever in laboratory having a scope and a signal generator and all, every year you should have you have to do in the calibration. Otherwise, it will give you the wrong information only. For that purpose, we used to do calibration in the radar, in the TX path as well as RX path. These are the 6 signals generating in the control room in a electrical domain. Now we have converted it to optical, that is going through optical cable, multimode cable. You can see here. So radar control, from the radar controller, IPP and the clock will be generated. To optical Ethernet will go to FT unit, fiber transfer unit. That unit is used to optical to electrical conversion is happening. That is connected to the TR module. Next, whatever received from the status of the TR module as a RX it will come. So next, IPP and clock. IPP and clock signal. These are all generation. Exciter will generate a 16 MHz clock as an electrical domain. Here we have a HFB component. There electrical is converted into optical. That is, this is the component called HFBR 14E6EZ or 4EZ using for TX. TX means electrical to optical. Again, this is for optical to electrical. 24E6EZ optical receiver. Right. So this is the some sort of group how we did one group. So that orange cable is called a multimode cable. Always in optical communication also you have to see whether long distance means you have to go for a single mode. Short distance communication means you have to go for a multimode. Generally in our radar we are using a multimode cable. Okay. Now I said no, so this is the one typical example I am saying antenna designing VHF radar. VHF radar, it is impossible to design microscope patch antenna. That is what we are using a Yagi antenna. Here I am showing that 2x2 antenna. This cable, this is top one is director. This dipole is the dipole, folded dipole. Then we have a reflector, down one. Next thing is that the black cable is that is for matching purpose. Lambda G by 2 cable is there for balloon matching. So 400 become 200 because of this folded dipole. Again, one more cable we are using. From that 200 is become 50 ohm for this TR model. This is the thing. Once now we are upgrading the antenna also. New antenna, this one. New balloon element we changed it. From that we check that performance. Operating frequency 53, you can see here minus 25.4 is the return loss. If you have a minus 24.4 return loss means nearly VSWR is 1.01 kind of thing. Exactly 50 ohm will be there. Same network analyzer, we have an option of Smith chart. But not shown here. We have a Smith chart also in that mode. In that Smith chart mode, where is the real part? That is whether 50 ohm or 48, 49. That is one. Whether it is having a inductive component or reactive capacitive reactance or inductive reactance, both will be there or not. We used to check in that continuous Z value, because we need not to see the R value. You have to show the Z value, the impedance. What to see. So this is the one output pulse, 8 microsecond output pulse, 1 kilowatt output. So this is the one GUI for this thing. I said this is the ping module ping, because that control card having a IP and all. Then this is a status, forward power, how much power it's radiating, everything will give. This programming and all coming from the FPGA card to radar controller. Okay. So this is the power meter. I said no, power meter. This is exactly 1 kilowatt. The 2500 watt power sensor is there. In that 2500 divided by 2.5 means 1000 will come. So this value will give a 1 kilowatt output. Next final topic now, recent development of SOC. Where SOC is there? So SOC, we have a 3 generation of sir. Hello. Hello. Sir, they're able to hear.
Sir, tell me, sir.
Yeah, okay. Some noise is coming. Whether
I will mute them, sir.
Okay, right.
It is muted, sir.
Yeah, okay, right, sir. So this is a SOC, latest designed that RF on the digital. Okay, so here now, like a computer generation, we have a generation 1, generation 2, generation 3 and all. So in generation 1, now we are doing in the generation 1 only. IF, we have up to 4 gigahertz, we can go for IF, generation of IF. That ADC also, we have a 12-bit resolution, and DAC is a 14-bit things are there. Next is generation 2. Now recent is up to 6 gigahertz, we can use as a IF generation from the digital chip. In olden days, for generating RF is a separate chip, that a DSP processor will be there for processing and generation and all. PLO technique, that and all used. That and all now we are using by using a FPGA. Same thing we did some project. So already I said in control card, Spartan 3 FPGA. 10 years back, Spartan 3 FPGA was there. Now that chip also obsoleted. Now any problems occurs, the TR model totally down. So that is not work. For that reason, we took a project, new FPGA called a Zinc processor. So previous chip was the Spartan 3. This is Zinc 7000 series. In that we took a project, then that also now through vendor we did it. So now we are able to produce a new cards also. This is the application of digital domain. Next, X and KU band weather radar. I said new radar is now ongoing project called X and KU dual band. Dual band means antenna also, dual frequency, all components, whatever we are using the FEM first end unit, front end unit, as well as excited signal or whatever maybe, that is the dual frequency. So 9.5 and 13.5 gigahertz. This is called I think weather radar. We are ongoing project, this one, because of our this SOC, RF SOC. From the RF SOC we are able to design exciter as well as signal processing. Both will be done by using this, because you will not disclose more the details about this, because this is an ongoing project. So this is the dual frequency, dual band and dual polarization antenna. One single antenna, it will work in the dual frequency. It is a horizontal polarization as well as vertical polarization. That is what a dual polarization antenna is there. That return loss, everything we checked, we fabricated also. 9x9 antenna we designed, now it is in the pipeline testing mode. So this is the one device called a FEM. Yeah, because I said any device you want to identify by using a spec. We are identified the spec in that techniques called a gallium arsenide technique, that power amplifier, the HMC 952, that chip we identify, core chip. In that core chip, that output is around 27 dB. ME is required. It will giving around 32 also, because this one chip will give the 0.5 watt. This core chip, one power amplifier, TR switch, and a limiter and LNA. 3 will be combined into the one chip. That chip is a LNH QPA 2609. This is the one that as a output of the our core chip output, and then This is the one signal processing I said exciter. Exciter. This is the evaluation board. That ZCU 111 evaluation board we purchased from Xilinx. From in that we developed our excited part. Resolution of 16-bit. You can see here reference given signal. We are giving 100 megahertz. From the 100 megahertz, we are able to generate 2 gigahertz as well as 70 megahertz. Whatever we want, we are able to generate. These are the specs. Now it is in the pipeline. That in that advantages in previous case we are taking one output. From the output we have to generate a different pulse scheme by using external circuit. But in the case of RFSoC, we can generate whatever waveform you like. You can generate like LFM and NLFM. We can generate. In weather radar, they used to see that simultaneously transmitter, alternately receiver, alternative transmitter, simultaneously receiver. Like that, different pulse scheme we can be able to generate from this chip. These are the output of our RFSoC chip. So 2 gigahertz we got it output. This is all simulation, not simulation. That evaluation board we developed now. In that from that board we got these outputs. So thank you, nice sir. So any query doubt is there, you can ask sir.
Thank you, Professor.
Yes sir.
Any queries you can unmute and you can ask the questions to the sir.